So, in this lecture we shall be looking at some features of blocking and non-blocking assignments which are not recommended to be used, like mixing both blocking and non-blocking statements in the same procedural block. This is the first thing we shall be looking at, and then we shall be talking about a feature in Verilog. There is a statement called generate, with which you can automatically and dynamically generate code in Verilog. So, we shall see these features in this lecture. Let us see. So, the first thing that we will be looking at very briefly, because this is not recommended, I shall not go into the detail. This is mixing blocking and non-blocking assignments within and inside a single procedural block. This I am not going into the detail because this is a very bad design practice. Okay. So, the idea is that the simulation and the synthesis tools that are available, they support using both blocking and non-blocking assignments inside the same always or initial procedural blocks. But again, like the examples that we took in the last lecture, there we looked at only blocking assignment, still then we saw that there are a lot of confusions. The order of the statements that you put, that becomes very important, which is not so for non-blocking. But if you mix them up, the problem becomes even more complicated, right. So, if you mix them up, the interpretation exactly what the circuit is supposed to behave like is not very straightforward, and hence it is not recommended. Okay. So, we shall be looking at two very simple examples, and I am repeating, such mixings should be avoided in an actual design. Okay. So, let us take a simple example like this. In the first example, we are using only blocking type assignments, always at star x equal to 10, x equal to 20, y equal to x, and then a delay of 10 here, and this is repeating. Okay. And here the last one we are using a non-blocking assignment. You see, for both these cases, what is the meaning? Blocking assignment means you first execute the first statement, 10 is assigned to x, then execute the second statement, 20 is assigned to x, then execute the third statement, 20 is assigned to y. Okay. So, this x will get 20 and finally, y will also get 20, both x and y will get 20. Now, in the second case you see, the first two are blocking, third one is non-blocking. So, the blocking statements, because they are not given any delay, they will be executing at time t equal to 0. So, at time t equal to 0, x will be getting 10 and then x will be getting 20 in this order, but both will happen at time t equal to 0 only. So, the final value of x will be 20, and this non-blocking assignment will take or evaluate the right hand side at time t equal to 0, and at time t equal to 0 this x has already become 20, because the time has not advanced, time is still t equal to 0 inside this loop. So, that latest value of 20 will be taken and the same 20 will be assigned. You see, this is actually quite confusing, you should not mix it like this, but if you use this you will see, if you simulate this, you can see that it is getting x equal to 20, y equal to 20, same value you are getting, right. So, this is one example, and the other example is that slightly different example, x equal to 10, y equal to x, x equal to 20, and here the middle statement we have changed it to a non-blocking assignment. Here let us see, the first one let us try to interpret. These are all blocking assignments. First x gets 10, then 10 gets assigned to y, then 20 gets assigned to x. So, the final value of x will be 20 and the value of y will be 10. But here what will happen? Here you see the order is important. The blocking assignment will interpret is that, well, once everything before me has finished, only then I will start. So, x will get the value 10, then it will wait, okay, because there is something before it. So, this 10 will be assigned to y, then this will come 20 will be assigned to x. So, this is again very confusing, but the simulator interprets it like this. If you simulate it using iVerilog, you will see that if you simulate both the designs, you will be getting the same result, x equal to 20 and y equal to 10. But I am repeating, you should not use this kind of mixing inside a procedural block. So, you will see some examples later, you will see that you can have multiple always blocks. So, in one of the always blocks you can use only non-blocking assignments, in some other always block you can use only blocking assignments. Such things are sometimes required in a design. We shall see later when you talk about designing sequential circuits, designing finite state machines and so on. Okay? Fine. So, we shall not be discussing any more on this. Now, we come to a very useful feature that is available in Verilog, which is called generate. Let me try to give you a brief motivation. What is this all about? Well, we took an example of a ripple carry adder earlier, if you recall. So, a ripple carry adder is constructed by simply connecting a number of full adders in cascade. The carry out of a full adder is connected to the carry in of a full adder, the carry out of the second is connected to the carry in of the third, and so on. So, if I want to design a 4-bit ripple carry adder, I will be connecting 4 such full adders. Now, if I want an 8-bit carry look ahead adder, I will be connecting 8 such. Suppose I tell you I want to design a 32-bit ripple carry adder, then means using the way which you have learned so far, you will have to instantiate the full adder 32 times, is not it? 32 copies of full adders are required and they will be connected like that. You will have to mentioning the carry values also, carry out will be carry in of the next one. So, 32 lines of code you will have to write. Now, you may think, so isn't it quite logical that the language should provide a feature of some kind of iteration or loop? So, I can say that I want 32 copies of full adder, I specify it only once and 32 copies will be generated. So, this generate block does exactly that. It dynamically creates multiple copies of your design or specification whatever you have written in Verilog to suit a particular design. So, we shall be looking at some examples. Generate blocks. So, there is a statement called generate. Generate is a keyword. Generate statements, as I mentioned, this allows the simulator or the synthesizer to generate Verilog code dynamically before they can be used. This is a very convenient feature to create so called parameterized module descriptions. So, I mentioned these parameters earlier, you can define a constant. So, you can define an n-bit ripple carry adder for arbitrary value of n. This is an example of a parameterized design. N is a parameter, you change the value of n, you get a 4-bit adder, 8-bit adder, 16-bit adder, whatever you want, just change the value of n. But the Verilog code remains the same, you need not have to change the code. The generate block will automatically do it for you, right. So, there are two keywords you require, generate and end generate. So, what generate block does is it creates some kind of instantiation of Verilog blocks number of times as you want. Now, these Verilog blocks that you can repeat or you can generate, they can consist of modules, user driven primitives, gates, continuous assignments, initial block, always block, anything, almost any kind of blocks you can use for this kind of repetitive generation. And also we shall see through some examples that when you create, say for example, multiple copies of the full adder, so each copy of the full adder will be given some name, so that you can refer to the signals in, for example, full adder number 5, the sum of the full adder number 5 you can refer to by a name, that name dot sum, which will mean that will be sum of that particular full adder. We will see how to do it. So, the generated instances will have some unique identifier names which you can refer, and these names are typically hierarchical. So, in order to use generate, you need some special variables which tell you how many times to repeat or generate. These are called Genvar type variables. The keyword Genvar is used for the purpose. So, you can use this keyword to declare such variables which are used only for the generation of the blocks. These variables will be ignored during simulation or synthesis. These variables will only be required or used during the generation of the code, right. And these Genvar variables, they are defined only within a generate loop and can be used there. And means I mentioned earlier that you can have a hierarchical naming convention, that every generate loop you define, you can assign a name to it, and that name by default can be used to refer to the variables of the generated copies. We shall see some examples how to do it, okay. But these are the basic ideas. So, let us straight away look at an example. This is the best way to think. Here we are taking a very simple example of a bitwise exclusive OR. Like, let us say what I am saying, I am taking a problem. Let us say I have a variable A, I have a variable B, which is multi-bit variable. Let us say this is 0 1 0 1, this value is 0 0 1 1, let us say. And suppose I am wanting to carry out bit by bit exclusive OR of these bits, and the result, let us call it f. So, 1 and 1, if you take exclusive OR, it is 0, 0 and 1 will be 1, 1 and 0 will be 1, 0 and 0 will be 0. So, this bitwise XOR, I want to do a parameterized design using Genvar, using generate, where I can use it for any arbitrary n, for any arbitrary n bit numbers. So, the idea is that if you want to do one XOR, one bit XOR, you need to make one instantiation of an XOR gate, like for example, A B that you can write XOR, you can give the name, say a name 0, then you can write F 0, A 0, B 0, like this. Then for the second bit, you can generate another XOR gate, XOR G 1, F 1, A 1, B 1, and so on. So, what I am saying now is that we want to define a parameter n, so that n copies of such XORs will be automatically generated. So, I do not have to write so many XORs. This n can be 32, 64, whatever, right. So, this is the example, let us see. This is my Verilog code and this is the test bench, this is the Verilog code. So, what I have written, let us see. This is the name of the module, 3 parameters, 3 are f, a and b, and here we have defined a parameter n, which for the sake of example we have taken it to be 16. So, a and b, these are the inputs, we are declaring it to be inputs from bit number 0 up to n minus 1, a and b, and similarly f is the output, similarly it is a vector 0 to n minus 1. And we are declaring a Genvar p, which p is a variable which we will be using inside this loop. Here you see use p. And this is how we can use a generate loop. Generate a for loop. Generate for p equal to 0, p less than n, p equal to p plus 1. It is exactly like a for loop, but it starts with a keyword generate and it ends with end generate, right. So, what it will mean is that whatever is there inside this begin end, this will be instantiated n times 0 up to n minus 1. So, what I have given inside this loop? You see I have defined a label, XOR LP is the label. I have given a label of this loop, and inside this I have instantiated one XOR gate. XOR I have given the name as XG, F this P, AP, BP. You see here we had given F0, A0, B0, F1, A1, B1. So, generally I am calling it as P, right. So, I call it BP, AP, FP. This is all. So, here if I just write this and I give it to the Verilog simulator or the synthesizer, it will be generating n copies of these XOR gates. So, here I have written it only once. So, suppose n is 16, 16 such XOR lines will be generated automatically. So, we have we can basically test this code out using a test bench like this. I have also showed a test bench, you can try it out. Here we have instantiated this XOR bitwise function. We just use this named convention of passing arguments. This f a b was here, and here in this test bench we are calling them x, y and out. Okay, x, y are 16 bits, out is a 16 bits. Initial we are monitoring x, y and out, and we are just applying two sample inputs. The first input is that first input x, you are applying a 16 bit hexadecimal number a, and y you are applying 00 ff, and after a delay of 10 we are applying x equal to 0f and y is 3333, finish. So, if you actually run this, you get an output like this. You see a and 00 ff. This a is 1010, you see 1010 a, 1010, 1010, 1010 and 00 ff, bit by bit XOR. 1 and 0 is 1, 0 and 0 is 0. So, the first 8 bits will be like this 1010, and the last one will all be inverted. 1 and 0 XOR is 1, 1 and 1 XOR is 0 and so on. So, this you can verify. And in the second test case, we have given 0f and 3333. So, 0 and 3 if you XOR it will be 3, f and 3 if you XOR it will become C 1100, then again 0011, again 1100. So, this is the simulation result. Now, you see this XOR LP and this XOR. Now, the point is that XOR LP, this was the name we had given to the generate loop, right. So, these 16 copies of the XOR gates that will be generated, we have given the name as xg, okay, but there will be 16 such gates. What will be the names? Because in this example I was trying to write, I was writing G0, G1, G2 like this, but here I wrote it only once xg. So, what will be the name that will be generated for the 16 copies of these OR gates? They will be like this XOR LP 0 dot xg, XOR LP 1 dot xg dot up to XOR LP 15 dot xg. So, whatever loop variable you have defined, that will be treated as a vector and you can use it with an index. Put a dot and whatever variable name you have defined, you can use it after that. So, like this you can uniquely refer to the 16 XOR gates, right. Let us take another example, just like the ripple carry adder I talked about. Well, we start by giving you a structural description of a full adder. This is a gate level description of a full adder that consists of 2 XOR gates, 2 AND gates and 1 OR gate. I showed this circuit earlier, you can just check it out. This is a compact gate level representation of a full adder. So, the first 3 parameters are the inputs, then sum and carry out. So, what we want to do now? So, we want to use it using generate to create an n bit ripple carry adder. Let us see how. This is the code. You see the code is so compact. See, this means we are not instructing this, we are just picking this code directly. You see these 3 wire and this OR and OR. So, whatever was this, we have directly picked up these 4 lines of code. So, these 3 temporary lines and these 3 gate XOR and an OR. So, here you see we are using a parameter n, let us say 8, we are creating an 8 bit adder. So, a and b are 0 to n minus 1, sum is also 0 to n minus 1, carry, there will be one carry means at the output of every ripple carry adder stage. So, it will be n minus 1 plus 1 carry out. So, that is why I am defining 0 up to n, and this last bit carry n, that is nothing but the carry out. I am just doing a continuous assignment using assign. Similarly, the carry in of the adder, that is your carry 0, the rest will be generated by the full adders. So, I have generated a variable genvar I, generate this loop again 0 to n minus 1, this is the name of the loop, FA loop, and the description, just the description which is given, same description here, right. Now, you see this generate will be creating 8 copies of these 4 statements are there, 4 lines. So, total 32 lines will be generated. Now, you see there are so many variables here, there are gates G1, G2, G3, G4, G5, there are some wires T1, T2, T3. So, how do you refer them for the copies? Same way, this FA loop 0 dot T1, FA loop 0 dot T2, FA loop 0 dot G1, FA loop 1 dot T1 and so on in the same way. So, this kind of hierarchical looping convention you can write. So, FA loop, this index you can use to indicate the copy number, you can indicate the gate number, the intermediate net number, anything you want, right. So, this is a very convenient way, this T will be small, okay, right. So, you see using this generate you can very conveniently represent some designs which are inherently iterative in nature, like this means adder is a very natural example. So, means whatever design comes to your mind which can be created by replicating or repeating the same building block a number of times, you can use this kind of generate statements very conveniently. So, it makes your module description very small and you are putting the responsibility on the synthesis or the simulation tool to expand them, right. So, with this we come to the end of this lecture. So, we shall be continuing with the discussion in the next lecture. Thank you.